Okay. Why is the sky blue? It does not have anything to do with the color of the ocean. Okay. So here's how this works. Um, our atmosphere is made up of 70% nitrogen gas. Okay. And it resonates, it being nitrogen gas. Let's do just resonates with higher frequencies of light, namely your blues and purples. And this is equal to the color of the sky. So we're going to say that light from the sun is white light. Okay. When it hits our atmosphere, my atmosphere is just crazy thick. I'm just doing this so we can draw some stuff. Our atmosphere is really thin in comparison, but it scatters the higher frequencies of light because of nitrogen gas. And I just want to apologize for the lack of colors I have here to represent this, but we're going to go with it. It scatters the higher frequencies of light, so the purples and the blues. And this is why we have a blue sky, because of nitrogen gas. It resonates, it's like, yeah, and like scatters, it causes photons to go, scatters. I should throw that out there. Causing it to scatter is the verb that we use for this process. Okay. Ooh, also, sorry, just thought of this. Delete number 3 on the review. We didn't cover it, nor are we going to take time to cover it. What doesn't get scattered is the lower frequencies. So we have green gets through. We're going to call this yellow gets through. Orange gets through. Red gets through. As we look at the color of the sun during the day, what color is it? Like a yellow. What color, what crayon color did you pull out to make the sun? Yellow. What color is made when you have green light and red light? Yellow. Good with that? So we see a blue sky and a yellow sun. Okay. The sun, if we went outside of our atmosphere and looked at the sun, it would look a whole lot more white than it does right now. Good with that? Okay. So these slides are telling us the same thing. All right. So if we were to graph the intensity of sunlight with respect to frequency, the different colors, what we find is the predominant color coming through our atmosphere is like a green-yellow. So this is this day glow color. We're going to call it chartreuse. That's why this day glow pops like boom. If you ever take yellow highlighter out during, like in sunlight, not in like an indoor but outdoors, like whoa, that's like so vivid. That's because it's capitalizing on the most intense frequency. Get to that. Hey. Oh, thank you very much. So give that one a shot. So if it is bigger, molecules are bigger, then it scatters a little lower frequency of light. What has a lower frequency of light than blue? Green. So green would get scattered, and what would be left over would be your yellow, red, and orange. So that would look orange. B. Yep. You okay with that? Okay. So we'd have a green sky and an orange sun. Okay. So what about sunsets? So in order for you to see a sunset, you are standing like right here as the sun goes closer and closer to the horizon. Sunlight has to go through a whole lot more atmosphere to reach your eye. The path that the light has to travel. Now, our atmosphere is made up of 70% nitrogen. There's other molecules like oxygen and CO2 and like carbon monoxide. Like there's just a lot of different things. There's also like dust particles and just other pollutant type stuff. So you have different sized molecules. The chances of sunlight being hit and scattered by these bigger molecules increases as the path gets longer. Does that make sense? And so that there are more different frequencies scattered because the chances of hitting bigger particles occurs. And so what you get is not only is it scattering the blues as normal and purples, but it also scatters the greens and the yellows. Some of the orange, and just the lowest frequencies get through. So that's why the sun looks deeper and deeper red colored as it approaches the horizon, and why the skies look really cool because it scatters the different colors. Good with that? We get the coolest sunsets when there's a lot of junk in our upper atmosphere. So if like a volcano erupts in the Philippines or forest fires happen in California, we get some really cool sunsets.
That sounds so unfortunate.
Yeah. So last summer we had some amazing sunsets because of Canada. Okay, because there's a lot of big chunks in our upper atmosphere. Okay, so this is why we have harvest or blood moons. Okay, these happen when the moon is near the horizon and it looks like a rust color. But as it raises higher in the sky, it becomes more and more white. Okay? And then I also wanted to bring up this whole idea of like, why is our sky the color it is? So this would be what I would consider an arid climate sky. I call this like a Colorado sky, like it's Arizona, Colorado, low humidity. This is good old Midwest. Okay, this is what our summer skies look like. It's more of a whitewashed. The reason being is we have a lot more humidity, which you've got water molecules in our air. We also that also attracts like dust particles, and so that scatters all the frequencies of light, making it more whitewashed. That's why clouds look white, is because they're made up of a whole bunch of different particles, and causing all the frequencies of light to scatter, making it white. Good with that? Okay. Just wanted you to appreciate what you see around you. Switching gears. Ready? Or not? Here we go. All right. Going through physics without talking about Einstein would just be a travesty. I'm like, you got to talk about it. You would have to talk about Einstein. So, speed of light. We know it's 3 times 10 to the 8th meters a second. That's fast. But how fast really is that? Well, in one Mississippi, light can travel around the Earth 7 times. Can travel around the Earth 7 times in one Mississippi, in 1 second. 7 times around the Earth. That fast. Okay? 1 second. That's how fast. Okay? Now, remember the whole thing with like, we had the basketball as the sun, and like how big is the Earth and how far away the Earth is from the sun, that whole lesson at the beginning of the semester. Okay? It takes light, the sun is far enough away from the Earth that it takes light 8 minutes to go from the sun to Earth. So if the sun were to stop shining right now, we wouldn't know about it for 8 minutes. So when we look at the sun, what we're seeing is the sun, what it was 8 minutes ago. You okay with that? Okay. So the nearest star with the whole basketball thing, like the sun's the basketball, how far or how close is the nearest star, would be Hawaii. It takes light 4.3 years to reach from Alpha Centauri to Earth. So if Alpha Centauri blew up right now, we wouldn't know about it for 4.3 years. So when we look at Alpha Centauri tonight, we're seeing what it looked like 4.3 years ago. Good with that? Okay. So before we go any deeper, have we heard of a light year? Okay, not buzz. Okay, this is the distance. that light can travel in 1 year. This is the distance that light can travel in 1 year. So, to give you a sense of this. So it's a distance, not a time. 1 light second is how far light travels in 1 second. That would be 7 times the circumference of the Earth. 1 light second would be 7 times the circumference, like the equator. Seven lengths of the equator. 1 light second. 1 light year is a huge distance. Alpha Centauri is 4.3 light years away from Earth. Oh. Oh. Like with what we have now, like it'd just be like a century. Maybe more. More. Definitely more. More. Millennia. Yeah. Take 1,000. Yeah. Okay. So that's the nearest star. In our Milky Way galaxy, I should look this up so I'm not misquoted here. What is the span distance across the Milky Way galaxy? About 100,000 light years. 100,000 light years. The distance across the Milky Way galaxy. So when we look across another star across the Milky Way galaxy, if it blew up, it would take 100,000 years for us to realize that. So when we see it tonight, we are seeing what the star was 100,000 years ago. So as we look into space, we're looking back in time. Good question. I don't know. Could be. Okay. So that's why, like the whole James Webb telescope, why there's so much money being put into this, because as we look deeper into space, we're looking back in time.
That's so weird. Like, would there be effects? Like, if a star blew up?
That far away, no. We could. What? If this guy blew up? Yeah, I think it wouldn't. Yeah. Yeah, it's a long. The chances of us getting hit by that would be super crazy small. Oh yeah.
Just blew up out of nowhere. What if Venus just like blew up?
Venus blew up. That would affect us.
Just a little bit.
Oh, not right away. So whatever the distance is, I'm guessing from Venus to Earth, probably about. Well, it depends on where it is in the orbit, but let's just say it would be 5 minutes ish.
Would we be able to see it like?
Oh yeah.
Clearly.
The explosion.
Yeah.
Oh yeah.
But if we're seeing something like 5 minutes.
Right.
Would we see it? So.
Would it affect us? Information. This is just bigger picture. Um, Gravitational waves travel at the speed of light as well. So we would see it and it would affect us at the same moment in time. Good question. All right. So Einstein's theory of relativity. So we're changing gears just a tad bit. Okay. So he came up with this idea, 2 postulates, 2 things that are true for his theory of special relativity to be true. Number 1, that all physical experiments can be repeated accurately so long as the frame of reference is at rest or moving at a constant velocity. It's a uniform frame of reference. What this means is this: I can sit here and at rest and throw this marker up, measure how long it's in the air, how high it's in the air, how fast it's in the air. I can do all these experiments with like projectile motion type stuff. And I can have the exact same experiment in a car going 70 miles an hour so long as I'm not changing speed or changing direction, and toss this up and have the exact same results. So long as my frame of reference is uniformly moving, like moving at a constant velocity. Those two frame of references completely agree on the experiments. Okay. And if you think about it, we are moving really fast around the sun. We're not at rest. And we're also moving really fast. The sun's moving really fast around the Milky Way galaxy. So at rest is kind of a relative term. You okay with that? And he's like, it's fine so long as everybody's moving at a constant velocity. Okay? That's postulate number one. Postulate number two says that the speed of light is constant 3 times 10 to the 8th meters a second, regardless of your frame of reference. Now, this one is, for most people, is easier to swallow, understand than this one. However, as you'll soon see in about 5 minutes, this one is the one that's wacky. This was the blue one is the one that breaks a brain. Okay, those two things. Ready? All right. So let's say we have a rocket, a spaceship that's able to travel at 300 meters a second. And then we have the missile that's also able to travel at 300 meters a second. Okay, the person on the ground, let's say you, is looking up here and going, yeah, 300 meters a second, 300 meters a second. So the question is, when these people look out the window and see this missile, how fast is that missile traveling relative to them? Let me break this down to something that's a little more relatable. You're driving on the interstate going 70 miles an hour. You see another car in the other lane driving also 70 miles an hour. How fast is that car going relative to you? An even simpler scenario is you're driving 70 miles an hour. How fast is the passenger, your buddy, your friend, riding in the passenger seat going 70 miles an hour in that same car? That person looks like they're at rest relative to you. You okay with that? That other car going 70 miles an hour looks like they're going zero. They look like they're at rest relative to you. These people see that missile traveling the same speed, so they see that relative to them, they're just zero. You okay with that? Okay, relative to the passengers, the missile is going 0 meters a second. Now, let's say we slow the rocket ship, the spaceship down to 200 meters a second. How fast do the people in the rocket ship see the missile going past them? They see them going past at 100 meters a second. So you okay with that? So bringing it back to like real life, if you're going 70 on the interstate and you look over to the person passing you and you can see on their speedometer like they got a big digital display 75 meters, sorry, not meters a second, 70 miles an hour, and they're going 75 miles an hour. As they pass you, that would be just as if you were parked and they were driving their car at 5 miles an hour past you. That's exactly what it would look like. You okay with that? Okay. So we're going to soup up this spaceship, and we're going to say it's going to go now 90% the speed of light. So like instead of going 3 times 10 to the 8th meters a second, we're going to go like 2 times 10 to the 8th meters a second. Okay. And we're going to shine a light out of a lighthouse. We're going to do the same question. From this person, us on the ground, we look at this going, whoa, that's going fast. Like 2 times 10 to the 8th meters a second. We clocked it. Radar gunned it. And we see light going past us 3 times 10 to the 8th meters a second. No surprise there. But when we ask, hey, folks in the spaceship, as you see light pass you, how fast is light going? Relative to you going 90% the speed of light. They see light not going 10% the speed of light as we would expect, but they see light going past them at 3 times 10 to the 8th meters a second as if they were standing still. Because Einstein said the speed of light is constant, is always 3 times 10 to the 8th meters a second, regardless of your frame of reference. Now, if that made sense, you didn't get it. That, when I said that, that should make you go, what? That doesn't make sense. Perfect. You got it. Okay. If that made sense to you, you completely missed it. Okay. Let me dig a little deeper here. Okay. We're going to do this little experiment. So we're going to have a spaceship. We're going to call this guy Adam and this lady Sarah. Okay. And we're going to say, okay, we're going to turn on the light bulb in the spaceship, and we're going to do a little experiment. The experiment is which wall gets illuminated first. If we had like super high-speed cameras that could document slow motion, like crazy slow motion, you turn on the light bulb, light travels, which wall is going to get illuminated first? Okay. From Adam's point of view, he turns it on, speed of light, the light waves go out at 3 times 10 to the 8th meters a second and illuminate both sides at the same time. Just like if you threw a rock in the pond, those ripples go out at the same speed. Bing. But if you ask Sarah, who's on the ground, she sees light going out at 3 times 10 to the 8th meters a second, but the back wall gets illuminated first because the back wall is coming closer to where the light bulb was, and so its distance that it travels is less. Bing. And then the wall is running away from it, has to travel more distance, gets illuminated after the back wall gets illuminated. Adam brings the spaceship around and they have a conversation like, same time, right? She's like, no, back wall got illuminated first. Like, what? Are you smoking? Like, I swear, like, this is like same time. She's like, no, it wasn't. It was back wall first and then the second. And I'm like, and so they have an argument and finally they're like, fine, you go try it. I'm like, I will. And it's like, so Sarah is now in the spaceship. She's same time. What? Adam was right. Adam's on the ground. Sees back wall, front wall. What? Sarah was right. How in the world? How can we explain that we have 2 different realities, 2 different observations with the same event? Okay. I'm not going to do that. Okay. So here's the deal. We think that there are certain measurements that we all agree on. Time being one of them. Like a second for you is a second for me is a second for somebody in China. It doesn't matter. Like, okay. We also assume length is consistent. We assume that mass is consistent. 1 kilogram here, in France is the same as here in the United States. Okay, that's like we all around the world over have this agreement. Like here's the base unit of time, here's the base unit of length, here's the base unit of mass. And Einstein's like, you know what? Let's just clear that off the table and not assume that. We're just going to assume that everybody agrees with that the speed of light is consistent for everybody else. That's where we're starting. And so the consequences of that is if you have a moving frame of reference, time slows down. A moving clock ticks slower than a clock that's a moving clock ticks slower than a clock that's at rest.
Wait,
What? Exactly. A clock that is moving ticks slower than one that is at rest. Okay. Now, before you start judging and trying to figure it out, let me just try to paint the picture here. Okay, so here is a light clock. Let me explain this. So you have two mirrors. For a clock, we need something that keeps a constant beat. Okay. We have two mirrors and we have a photon going between these two, bouncing. Certain distance between these two mirrors. Okay. And so even though it's a fast tick, it's still a consistent measurement. Does that make sense? And we can use that to measure time. It's a light clock. Okay. Now, Sarah is going to have her own light clock. Adam is going to have his own light clock. Okay. And here we go.
At the ground, which bounces off a mirror, and he measures the time it takes for the light to return to the spaceship. From Adam's perspective, the laser light goes straight up and down. From Sarah's perspective, the laser light follows a V-shaped path. The V-shaped path is longer than the straight up and down path. Since the speed of light is the same for all observers, from Sarah's perspective, it takes a longer amount of time for the laser light to return to the spaceship. But if Sarah looks at Adam's clock, she will see that his clock reads less time in between when he fired the laser and when he received the reflected light back. This means that Sarah will see Adam's clock running slower than her own clock. The closer that a spaceship approaches the speed of light, the slower the time inside the ship will flow. If the speed of the spaceship was equal to the speed of light, then time inside the ship would stop altogether. No matter how fast the spaceship travels, Adam will never notice that time for him is going slower. Everything is slower by the exact same amount, including the speed of his thoughts. So time for Adam appears to be flowing normally.
Okay.
So the closer you get to the speed of light is slower clocks move because you're getting closer to equal it, so
Yep.
your clock will eventually stop altogether.
Yes.
Why? Wait, so real no time.
Okay, hang on to that thought. Okay, let me unpack this light clock. Okay, so each tick, the time duration is the distance divided by the speed of light. Okay, Sarah's clock on Earth agrees with Adam's clock. How Adam observes it, he sees the same thing. What gets weird is when Sarah looks at Adam's clock. That's what gets weird. Okay, because Sarah sees Adam's clock go this from here to here, covering a bigger distance, a longer distance than hers. And so because this distance increases, the time difference, the time interval between ticks is greater. So Sarah sees her clock going, sees Adam's clock going, so she sees Adam's time or clock tick slower. Okay. First time I heard this, I was like, get a real clock. This is absolutely stupid. Like, where's the Timex? Like, give me something with hands and hours and gears and stuff. And it's like, doesn't matter. It's not the fact that the clock is ticking slow, it's the fact that time is progressing slower as you move closer to the speed of light. Now, if you're in that frame of reference, you don't see that. It's only when you compare one person's point of view compared to the next. Okay, so we've tested this couple ways. We took two atomic clocks, like super accurate clocks, to like umpteenth decimal place. We synchronized them. We put one in a jet, flew it around for several days, parked it. The one that was moving, that was in the jet, was a tad bit slower than the one that was at rest on the ground. Okay. Why we don't see this at appreciable levels is because we don't go that fast. Time dilation only occurs as you get appreciably occurs as you get closer and closer to the speed of light. The fastest we've ever made anything man-made to go is somewhere like over here, like bullets, satellites, spaceships, rockets, anything. Like we are like super duper slow in comparison to the speed of light. Okay, so we don't see that effect as much. Braden.
Okay, so this is kind of weird, but what would happen if you were to go faster than the speed of light?
Okay, hang on to that thought. We might get to that. All right, so another another reference point was a muon. A muon is a subatomic particle. We've created them in particle accelerators before, and they last like their lifespan is like microseconds. Like oh, we saw it, it's gone. But we see them in nature lasting for several seconds. Like what gives? Like why? It just doesn't live well in captivity. It's like no, the speed of a muon was really close to the speed of light, and so from our point of view at rest on Earth, their clock was ticking slower. And so from our point of view, they lasted longer because their time for them was their clock, their lifespan was a lot longer because time was progressing slower from their point of view. Okay. So, I don't worry about that. Okay. So, If you had, this is known as the twin paradox. If you had a twin and you stuck them in a spaceship that went close to the speed of light and they returned in 20 years, they'd come out of the spaceship having only experienced 10 years, let's say. Yep. Yep.
You put them in a spaceship for how long?
For our point of view on Earth, 20 years. They come out and like, man, those 10 years have been rough on you. I'm like, yeah, I'm almost 40. Are you kidding me? I'm almost 30. Because because they were moving close to the speed of light, so their clocks were ticking slower. They experienced, and so you have this argument like, dude, it's been 20 years. Like, no, it hasn't. Like, look, here are my kids. They're almost graduating from high school. I'm like, what? And like, and they like measure their compare their logs and their journal entries, like 10 years worth of entries, 20 years. They like looked at, like, they had some heart monitors, and the person on Earth had like 20 billion heartbeats, and the spaceship dudes only had 10 billion heartbeats. Half them, like, every time slowed down for the one that was going close to the speed of light. Okay, because they're moving. Okay, this is not just theoretical. So we have had GPS uses satellites. Satellites are going pretty fast, not crazy fast, not speed of light fast, but fast enough. And the distance between the Earth and the satellites is big enough that they couldn't pinpoint. They were like missing. Their accuracy was off by something. Like, what is going on? And someone was like, these satellites are moving kind of fast. Maybe we need to incorporate Einstein's theory of special relativity to like see if that fixes it. And you know what? It did.
Einstein was crazy.
Einstein was, but he was crazy smart. Okay, so it's legit. Okay, so this explanation helped me swallow this a little bit better. So we live in 4 dimensions that we dabble with consistently: length, width, depth. The 4th dimension is time. Einstein said, hey, these 4 dimensions, this is space-time. Every object is traveling at the same speed through space-time. Okay? If you are at rest, you're not traveling at all through space. All your space-time velocity is going through time. You're traveling as fast as you are through time when you're at rest. But as you get moving through space, that's taking some of your space-time motion and going through space and taking away some of that from time. So the faster you travel through space, the less you're traveling through time. So the point at which you're traveling at the speed of light, which is as fast as we can travel, you're not traveling through time.
There be a part where you said the faster you travel through space is
Yeah.
you travel through time?
Yep, because the amount of your speed through space-time is a fixed amount. Okay, and so the faster you travel through space, the slower you travel through time. Okay, so light does not experience time because it's going the speed of light. Now, here's some other crazy things. So length isn't consistent. As it turns out, as you do, like you dive deeper into the math, length constricts. As you go faster and faster, a meter isn't this long, it's like this long. Mass increases as you go faster and faster. And so there's this conundrum that as you go faster, you get more massive. Well, to make something more massive speed up more, you need more energy. And it turns out when you're, according to the math, if you're going the speed of light, you have infinite mass. In order to make something that's infinitely massive speed up, you take an infinite amount of energy, which doesn't exist. So anything with mass can't go to the speed of light. according to Einstein. So, Braden, to answer your question, from Einstein's point of view, we cannot go, because we have mass, faster than the speed of light, or even the speed of light. So, stuff with mass cannot go. Now, what they are trying to propose, let's see if there's anything else. I think we have time for this. Okay. What we're trying to propose is this. Light cannot travel faster than the speed of light through space. But what happens if we warp space? Then we could, like, the speed limit still exists, but we're changing the medium through which space or light travels. We could change that. And so that's what we're trying to experiment with, to travel, like sci-fi movies going warp whatever. We've warped space in order for us to travel really fast, even though we're not crazy, right? So, last thing at you, you can't go through physics without talking about E equals mc squared, like the most popular equation for someone who's never taken physics. Like, what do you know about physics? I don't know. E equals mc squared, right? So this was this is kind of like the energy mass equivalency type thing. So let's say the nucleus of an atom, and it has a mass of 5. You break that apart, a lot of energy is released, atomic bomb stuff, okay? And then you measure the two halves. This was 5. Now it's not 2.5, 2.5 as we would expect, but it's like 2 and 2. Like, what happened to the extra 1? Well, it got converted into energy. How much energy? It's based upon this equation. Okay, so it took mass and it was not dissolved, or like, but like it, I don't know if converted is even the right word, into energy based upon the, and how much based upon this equation. So a little bit of mass times the speed of light squared, not something's moving twice the speed of light or anything like that. It's just the equation that works, that makes this work. Speed of light squared is equal how much energy is given. Boom. There you go. That's that.